Okay, let's unpack this. You sent us some truly fascinating sources, all revolving around game-based learning. And from what we can tell, you're particularly interested in how these cutting-edge insights apply directly to elementary education. What an exciting and frankly transformative frontier to explore. Today, we're embarking on a deep dive into the surprising power of action video games. Yes, those fast-paced, often misunderstood digital adventures. And how their core design principles aren't just for entertainment, but can actually enhance broad cognitive abilities, skills absolutely crucial for young learners. Our mission, should you choose to join us, is to extract the definitive secret recipe from this research. We'll show you how to move beyond simple educational games and instead harness the very design mechanics that make any game so powerfully engaging and effective for learning, especially in an elementary school setting.
Indeed. What's truly fascinating here is how these sources fundamentally challenge our traditional understanding of learning, particularly the long-standing and quite persistent issue we call learning specificity. For a very long time, we've observed that skills learned in one precise context often, stubbornly, fail to transfer, even to slightly different situations. This has been a real headache for educators, for rehabilitation specialists, and frankly, for anyone trying to apply knowledge in daily life because, well, genuine generalization is so incredibly crucial.
It really is. I mean, if a student masters a skill in one specific way, how do we ensure they can actually use it flexibly when the situation shifts even a little bit?
Exactly. That's the initial puzzle we're grappling with today. And this is precisely where action video games, quite unexpectedly, enter the conversation. They offer a powerful clue about how we might design learning experiences with a much broader, more generalizable impact.
So let's really peel back the layers on this concept of specificity of learning. It might sound like academic jargon, but it's actually quite intuitive when you start thinking about it, right?
Yeah, absolutely. At its heart, it's the idea that when you learn a skill in a very precise, maybe narrow environment or context, that skill often doesn't automatically transfer. It doesn't move well to even slightly different situations. It's like your brain becomes hyper efficient at that one thing in that one setting.
But it doesn't build a flexible, transferable understanding.
Precisely. Our sources give some excellent, almost counterintuitive examples of this. Imagine a vision task, what's called a vernier acuity task. Someone is trained rigorously to judge whether two horizontal bars are perfectly aligned. They practice, they get incredibly, almost superhumanly good at it.
Okay, makes sense. Practice makes perfect.
Right, but here's the twist. If you ask them to perform the exact same task, the very same alignment judgment, but with vertical bars instead of horizontal ones, their performance surprisingly drops right back down to that of someone who's never practiced it at all.
Wow. Really? Just changing the orientation.
Just changing the orientation. It's as if their brain has learned a hyper-specific trick for horizontal lines, but not the general skill of, detecting alignment.
That's wild. It really shows how specific that learning can be.
And that's not an isolated quirk. Consider the even more compelling example of experienced Go players. Go is an ancient, incredibly complex board game renowned for its strategic depth. These masters can recall briefly presented Go board displays with truly astonishing accuracy, almost like taking a mental snapshot.
Yeah, I've heard about that. It's amazing.
It is. They've developed this phenomenal visual memory specifically for Go game states. But when they're tested with Gomoku displays a much simpler game that uses the same board and pieces, their memory performance is no better than someone who doesn't play either game.
Even with the same board and pieces.
Yeah.
That's incredible.
It's a classic, almost painful demonstration of how deep expertise in one domain doesn't automatically transfer, even to closely related ones. Because the underlying cognitive model of the game, how the pieces interact and the board dynamics, it's different. And for educators, this vexing issue of specificity means that simply teaching a child to, say, memorize multiplication tables in a rigid drill and practice format doesn't guarantee they'll know how to apply those same multiplication skills.
Right, like when they're trying to figure out how many juice boxes are needed for 3 classes of 25 students, or how much wallpaper to buy for a classroom project.
Exactly. Generalization is absolutely necessary for any real-world impact, for learning that sticks and can be used flexibly in novel situations.
That Go example really hit home for me because it shows just how narrowly our brains can optimize. It's almost scary. And if we connect this directly to the elementary classroom experience, think about a challenge nearly every teacher faces. A student who masters addition facts using flashcards. They get every single one right, practically reciting them in their sleep. But then they struggle significantly when those same addition skills are embedded in a word problem, right?
Oh, absolutely. Or a real-world scenario like calculating change for purchase at a school bake sale.
Exactly that. That right there is learning specificity in action. Their brain has optimized for that specific flashcard context, or that particular visual cue and response.
But the underlying skill hasn't generalized to a slightly different presentation or a more abstract application.
Yeah. The source highlights that traditional training, precisely because it often emphasizes repetition in fixed contexts, tends to lead to these very narrow improvements. You get good at that exact thing, but the learning doesn't readily spill over into other domains.
And this brings us to the surprising, almost counterintuitive solution that has emerged from recent research: action video games, or AVGs. Over the last 15 years, a growing body of scientific evidence provides compelling proof of a beneficial and remarkably broad impact from playing these games across various subdomains of cognition. We're talking about areas like perception, top-down attentional control, and spatial cognition.
Okay, so foundational stuff.
Foundational, yes. While the research notes that there have been fewer studies explicitly investigating higher-level skills like complex reasoning or problem-solving skills, often directly linked to academic achievement, the evidence for foundational cognitive skills is exceptionally strong. The types of AVGs most often studied include first- and third-person shooter games, like Call of Duty or Halo. They were among the first to show a positive impact on attentional control.
Right, the ones people often think of first.
Exactly. But the research also points to other genres with similar underlying mechanics. Things like real-time strategy games, StarCraft, for instance.
Oh, interesting, like managing resources and units quickly.
Precisely. Or driving games like Need for Speed. Even potentially action role-playing games like Skyrim or Final Fantasy. It seems to be about those fast-paced, multifaceted decision-making elements that they share.
So let's talk about the initial evidence for this impact. How did researchers first start noticing these connections? Because it seems, well, maybe unexpected.
It certainly wasn't the prevailing view initially. The sources point to a number of cross-sectional studies. These are studies that compare groups. Typically, self-declared habitual AVG players, usually defined as individuals who play first- or third-person shooter games for at least 3 hours a week and have been doing so for at least 6 months.
Okay, so pretty regular players.
Yes, compared with individuals who have little to no video game experience. And what they found is truly eye-opening. AVG players typically show better visual abilities. For instance, in terms of contrast sensitivity, how well you distinguish subtle differences in light and dark.
Like seeing things more clearly.
In a sense, yes. Or crowding acuity, how one can see objects when they're sort of crammed together in a cluttered visual field. They also exhibit significantly enhanced attentional control, meaning they're better at visual search tasks, more efficiently recovering from misleading cues.
Like not getting thrown off by distraction.
Exactly. And remarkably adept at filtering out distractions during demanding cognitive tasks. Benefits have even been noted in mental rotation tasks, manipulating objects in your mind, visuospatial working memory, and complex task-switching paradigms.
Wow, that's quite a list of cognitive improvements.
It is, and this isn't just a collection of isolated observations. It's robustly backed up by significant meta-analyses. These combine data from many studies to get a clearer, more powerful picture. A major meta-analysis by Bediou and colleagues in 2018, for example, compiled data from close to 3,800 participants. They found a positive impact of about half a standard deviation specifically, a Hedges G 0.55 across 7 distinct domains of cognition for habitual AVG players compared to non-video game players.
Half a standard deviation. Okay, put that into perspective for me. For an elementary teacher, what does that kind of number mean in practice?
That's a great question. Think about it like this. Imagine a child who consistently struggles with focus in class. An improvement of half a standard deviation could mean moving from being average in focus to being in the top 30% of the class for that skill. It's a substantial, observable change, not just a tiny blip.
Okay, that helps. That's significant.
Definitely. The most reliably enhanced domains were attentional control, spatial cognition, perception, and multitasking. While the enhancements were weaker, they were still statistically significant for inhibition and verbal cognition, highlighting the remarkably broad impact of AVG play.
Broad is the key word there, it sounds like.
Very broad. The only area where firm conclusions couldn't be made due to limited sample sizes was reasoning and problem solving. The researchers explicitly said this calls for more dedicated studies in that area.
That's a crucial point, and it's one that often comes up when we discuss these topics.
Yeah.
So while we're seeing these strong foundational cognitive benefits, it sounds like there's still a frontier for research on how these games directly influence higher-level skills, like complex reasoning or creative problem solving. Expert, what does that mean for an elementary teacher? Should they manage expectations, or does building these foundational skills naturally pave the way for those higher-order ones?
It's a bit of both, really, and it's an important distinction for educators. The research strongly suggests these foundational skills like attentional control, processing speed, visual spatial abilities are indeed fundamental prerequisites for higher order thinking.
Like you need the building blocks first.
Precisely. You simply can't effectively solve a complex multi-step problem if you can't filter out distractions, or if you struggle to hold multiple pieces of information in your working memory simultaneously. So, while the direct causal link to complex problem-solving within game contexts needs more dedicated studies, the evidence strongly implies that by strengthening these building blocks, we're inherently setting children up for greater success in those higher-order areas.
So it's still a very worthwhile investment, even if the direct link to, say, complex math problem solving isn't fully mapped out yet.
Absolutely. It means educators can confidently explore games and activities that build these foundational cognitive muscles, knowing they're investing in a broader academic potential that supports the development of more complex skills, while still keeping an eye on the evolving research regarding more direct impacts on, say, abstract reasoning or truly novel problem-solving skills.
Now, cross-sectional studies like those are fantastic for showing correlations that AVG players tend to have better skills. But that doesn't prove causation, does it?
Not definitively, no. That's a classic correlation versus causation issue. Maybe people with better attention are just drawn to these games in the first place.
Exactly. So to truly prove a causal link that playing the games causes the improvement, you need something much more rigorous. Intervention studies. That's where the scientific rubber really meets the road, right?
Exactly. This is where randomized controlled trials, or RCTs, come in. They're really the gold standard in establishing causation. These studies are meticulously designed to rule out population selection bias or other confounding factors that could cloud the results. Participants are randomly assigned to one of two groups.
Okay, so no self-selection.
Correct. You have an experimental group, which trains with action video games for a set period, or a control group, which trains with non-action video games. Both groups are thoroughly tested before and after the training period to precisely measure any changes in their cognitive performance.
And the control group plays other games, not just like sits around.
Right, that's key. Both groups are playing commercially available entertainment titles, but they leverage very different underlying mechanics. While the experimental group plays fast-paced shooter games, control groups play things like puzzle games. Tetris is a common one, or social simulation games like The Sims, or even slower turn-based strategy games like Restaurant Empire or Balance.
So you're controlling for the video game playing aspect itself.
Exactly. The key finding, time and again, is that the action-trained group consistently improves more from pre-test to post-test across a range of cognitive measures. This interaction, the difference in improvement between the groups, is absolutely crucial for establishing the causal impact of AVG play on cognition. It moves us beyond mere correlation.
And another pivotal meta-analysis from Bidieu et al. In 2018 specifically probed this causal impact, didn't it?
Yes, they did. They meticulously combined data from 609 participants across multiple intervention studies, all adhering to that rigorous RCT active control design we just discussed. They found that the causal impact of AVG play on cognition was indeed significant, although the effect size was a bit smaller. Hedges G is 0.34.
Smaller than the cross-sectional studies. Why is that?
Well, that's entirely expected, actually. First, the exposure times in these controlled intervention studies are relatively shorter compared to habitual players who play for years. And crucially, remember, the control group was also playing video games, just different types. So you're comparing AVG training against other game training, not against no training at all.
Ah, okay, that makes sense. The tougher comparison.
It is. But what's truly striking is that, in line with the cross-sectional results, the greatest impact from action video game training was consistently on attentional control and spatial cognition, with promising signs for perception. This powerfully reinforces the idea that the impact of AVGs is, as the source says, rather wide compared to the typical high specificity of learning we discussed earlier. It's a compelling counterexample to that very vexing problem of learning, not transferring.
So the interventions really back up the idea that these specific types of games cause these broader cognitive benefits.
Yeah, they do. These intervention studies consistently highlight that action video games enhance cognition more broadly and effectively than these other, often slower-paced, less attention-taxing genres. This gives us truly important clues about the key game features that are supporting these broad cognitive enhancements. Video games are, after all, our most advanced and engaging virtual environments. And while designed primarily for entertainment, certain categories are clearly incredibly effective at improving cognition. So researchers are essentially trying to reverse engineer them, contrasting effective games with less effective ones to pinpoint the precise action game-specific features that drive these changes.
The secret recipe we talked about at the start.
Exactly. Our sources propose a non-exhaustive but highly insightful list of 6 main design principles, helpfully divided into 2 categories. 3 principles that are general to any truly well-designed learning experience, and 3 that seem particularly optimized and perhaps uniquely potent in action video games.
Okay, this sounds like where the practical takeaways really start to emerge for someone thinking about elementary education. What does all this dense scientific research mean for us, especially in the context of designing learning for young kids? The research points to this secret recipe. Specific game features that, when combined in the right way, foster broad cognitive enhancement that extends beyond just playing the game. And the very first key ingredient in this recipe, a principle applicable to any well-designed learning experience, digital or analog, is what they call being in the zone of proximal development, which basically means providing adequate dynamic scaffolding of level difficulty.
That's absolutely right. Games are only truly fun and engaging to the extent that they are challenging, yet still feel entirely doable. It's a delicate balance. Think about how virtually all successful video games are structured. They start easy enough not to discourage new players, providing quick wins and building confidence. But then they continuously, almost imperceptibly, increase in complexity and demands to keep players engaged and genuinely interested.
That gradual ramp up.
Exactly. This concept of scaffolding in video games is beautifully illustrated with the puzzle game Portal. Remember that one?
Oh yeah, brilliant game with the portal gun.
Right. You begin with nothing but your wits. Then you're introduced to the concept of portals themselves. Next, you acquire a portal gun that initially only controls one portal, letting you grasp the basic mechanics. Much later, you learn to control both entry and exit points, opening up vastly more complex problem-solving possibilities. Each test chamber or puzzle methodically builds on knowledge and skills acquired in earlier ones, gradually increasing in complexity.
Keeping you challenged but not overwhelmed.
Precisely. This precise scaffolding keeps players deeply engaged because initial puzzles are simple and subsequent ones are only slightly more difficult, always appearing solvable with just a little more effort. And crucially, this methodical incremental scaffolding ultimately allows players to solve highly complex problems that they likely wouldn't have been able to tackle without that carefully managed incremental training.
And in psychology and education, this notion of scaffolding is directly linked to Lev Vygotsky's foundational concept of the zone of proximal development, or ZPD. For elementary teachers, this isn't just theory, it's a core pedagogical concept, right? That sweet spot.
Exactly, that sweet spot. The range of abilities a student can reach with appropriate external support. Something neither too easy, which leads to boredom,
or too hard, leading to frustration and giving up.
Precisely. It has to be just right to encourage genuine growth and mastery. Providing adequately personalized learning experiences that are constantly adapting to be within that ideal zone, is a critical component for optimizing learning. The research even shows that games where difficulty adapts to the individual player, for instance, constantly maintaining a challenge level where players are performing around 80% correct, pushing them just enough.
Kind of keeping them on their toes.
Exactly. Those games consistently yield greater cognitive benefits than games where the difficulty level is fixed at a non-challenging level, or is simply overwhelming.
But there's a catch, isn't there? It's not just about making it harder.
That's a crucial nuance, yes. What's critical isn't just that the difficulty adapts, but what dimensions or cognitive processes that scaffolding is applied to. It's not enough to simply make a task harder in a superficial way. For example, in the NeuroRacer game study we mentioned earlier, one group played a multitasking version, while another played single tasks, both at equally challenging levels, maintaining that 80% correct performance. But only the multitasking group showed broad cognitive benefits.
Ah, so the type of challenge matters enormously.
Enormously. Similarly, with the real-time strategy game StarCraft, Only the version that required controlling multiple bases and greater multitasking led to improvements in cognitive flexibility, even when both versions were designed to maintain a 50% win rate. These examples illustrate that simply maintaining the learner through increased challenges is insufficient. The challenge needs to load on higher-order cognitive resources like cognitive flexibility, working memory, and speed of processing.
Not just making you click faster or something simple like that.
Right. It's about challenging the thinking, not just the doing.
Okay, let's make this concrete for an elementary classroom. Imagine a digital reading fluency game for second graders. Instead of just having fixed levels where every student reads the same static list of words, a game leveraging this principle of scaffolding would work how?
Well, it would adapt. If a student masters reading CVC words, consonant, vowel, consonant words like cat or dog, quickly and accurately.
Instead of just giving them more CVC words.
Right. The game would automatically introduce words with silent E or vowel teams like boat or rain, gently but firmly pushing them to the next level of phonetic complexity. If they struggle with those, it provides more adaptive practice with CVC words or even breaks them down into individual sounds with more support.
Or maybe a math game for fractions. It starts with simple pie charts.
Then as they master those, the game dynamically introduces fractions on a number line, then fractions as parts of a set. Each new representation builds on the last but requires a slightly different way of thinking.
So it's this personalized, adaptive challenge that keeps them engaged and learning effectively within their ZBD.
Exactly. Much like how Portal gradually empowers players to solve increasingly complex physics puzzles. The key is that the challenge is tailored to their specific, evolving cognitive capacities, keeping them at that optimal edge of learning, always asking just a bit more from their brain.
Got it. Principle 1. Scaffolding within the ZPD, focusing on cognitive load. What's next?
Our second general principle for effective learning games is all about reward structures and adequate feedback. Many researchers emphasize the critical importance of immediate feedback in video games, not just for learning specific actions, but also for supporting that state of flow where you're completely immersed.
Yeah, losing track of time.
Right. But video games typically have incredibly complex, multi-layered reward and feedback structures. It's not just one thing. You have very immediate feedback, like the visual and auditory confirmation of a hit or miss when you shoot an enemy, or a satisfying clink when you collect a coin. Simple, direct cause and effect.
Okay, instant gratification.
To an extent. But you also have delayed, far more complex rewards, like the completion of a long quest line after many sequences of actions, where you're never explicitly told if a different path would have been better or faster. In a game like Call of Duty, you make countless choices in a split second, but the game doesn't tell you the alternative actions that would have led to better results.
You have to figure that out yourself.
You have to explore, experiment, and figure it out yourself through experience. Much like a chess grandmaster learns from playing countless games, rather than being given a detailed blueprint for every move.
This directly connects to core learning theories that are super relevant to education, doesn't it? Like supervised versus reinforcement learning.
Absolutely. In machine learning, for instance, you have what's called supervised learning. This is where you're given full, immediate instructional feedback, essentially. The correct response is provided for every single input. Think of it like flashcards where the answer is immediately on the back.
Okay, tells you exactly what to do.
Yes. This leads to fast acquisition of specific skills, but often with very limited generalization, because the brain isn't forced to figure things out for itself. It's great for what's called model-free learning, which is essentially habit formation, building quick stimulus-response connections.
Learn the rule, apply the rule.
Pretty much. Then you have reinforcement learning, where you get evaluative feedback, a reward signal, maybe points or progress, but you're not told the best response. It's like a treasure hunt where you know if you're getting warmer or colder, but you don't have a map.
So you have to explore more.
Exactly. This forces exploration, trial and error, and encourages the building of rich internal representations or models of the world, which is absolutely crucial for genuine generalization. The trade-off is clear. Immediate, detailed feedback can speed up the learning of specific actions, but it might actually limit the brain's ability to build those flexible, transferable mental models.
Those models are the key to applying knowledge in new situations, right?
You really are.
Okay, so how does this feedback principle play out in an elementary setting? This seems really nuanced.
It is incredibly relevant and nuanced for elementary teachers. For instance, imagine a phonics app. If a student matches a letter to its sound, immediate visual and auditory feedback like, "Great job, that's the P sound," reinforces model-free learning. Quick acquisition of a specific association, that's valuable for foundational skills.
Okay, good for nailing the basics.
But now, consider a science simulation where students are experimenting with different variables to see how plants grow. They might adjust light, water, soil composition. The feedback here might be slower and more evaluative. Perhaps a message like, "Your plant is wilting. Try adjusting the light exposure over the next simulated week."
It doesn't just say, wrong, add more light.
Exactly. This kind of feedback doesn't give them the right answer directly. Instead, it encourages model-based learning. It forces them to build an internal model of plant needs and the cause and effect relationships, and then apply that understanding to new situations rather than just being told the right answer.
So it makes them think more deeply about why.
Yes. It compels them to explore, hypothesize, and build a deeper, more transferable understanding. Similarly, in a digital storytelling game, if a child is prompted to write a sentence and then gets immediate feedback on every spelling error, that's model-free, good for spelling. But if the game provides more holistic feedback on the story's coherence or character development after the entire narrative is complete, that forces the child to refine their understanding of storytelling principles, a more model-based approach.
So the type of feedback really depends on the learning goal. Speed versus generalization.
Precisely. And it's also worth noting that while negative feedback, like a wrong answer notification, can drive immediate correction, positive feedback rewards, encouragement is key for maintaining long-term engagement and motivation. But too much feedback, or feedback that isn't well aligned with the learning goals, can actually overload or distract the player, ironically hindering the very cognitive enhancement we're aiming for.
Finding that balance again. Okay, principle 3, information load and variability. This sounds interesting. What's the core idea here?
The core idea is that for learning to generalize, the learning environment needs to have enough complexity and unpredictability to prevent the brain from just going on autopilot. Our sources use a brilliant contrast to illustrate this. The classic puzzle game Tetris versus the dynamic team-based shooter Team Fortress 2.
Ah, okay. Big difference there.
Huge difference. In Tetris, the game state is almost entirely visible, static, and deterministic. All the relevant info is right there. The falling pieces behave predictably. The only random bit is the next shape. You control one shape, limited actions. Overall, the amount of information you need to process and manage is quite limited.
Right, it becomes almost automatic after a while.
Exactly. This structure allows for rapid automatization, essentially. Your brain develops a very efficient lookup table for optimal moves. You get so good you don't even have to consciously think anymore. You just react. And what happens when you automatize something to that degree? Limited transfer.
Back to specificity.
Yeah. Expert Tetris players don't suddenly have universally better mental rotation skills unless they're tested with Tetris-like shapes. Their skill is highly specific.
Okay, so what about Team Fortress 2?
In stark contrast, Team Fortress 2 throws a truly vast amount of information at players in a constantly shifting environment. You're part of a team, coordinating actions against another team, complex social and strategic thinking. 9 distinct character avatars, each with unique skills, weaknesses, requiring different playstyles.
Lots of variables.
Tons. Varied, complex maps you need to understand spatially. Crucially, you only ever have partial information about the game state. You don't always know where opponents are or their exact status. You have to infer and predict. And most events are probabilistic, not deterministic. You can't always predict exactly what will happen.
So it's messy, unpredictable. Like the real world.
Exactly. This rich, dynamic, and partially uncertain environment actively prevents full automatization. It constantly keeps attentional resources, cognitive flexibility, and inhibitory control in high demand because you can never truly zone out. The importance of variability is precisely this. It acts as a cognitive workout, preventing your brain from settling into rigid, automatic patterns.
Which is crucial for generalization.
Absolutely crucial. Games need to present enough variability in terms of information, threats, opportunities to prevent the brain from going on autopilot and releasing the demand on attention and cognitive control. Think about the Bunnies Can't Jump minigame from Rayman Raving Rabbids, where players jump rope at varying unpredictable speeds while ignoring distractions. It directly emphasizes maintaining flexible attention in a highly variable yet structured environment.
That Tetris versus Team Fortress 2 analogy really paints a clear picture. So let's bring this into the classroom again. Think about a classroom spelling activity for an elementary student, a traditional drill and practice app.
That presents words one at a time with clear, consistent feedback for each correct letter. That offers low information load and very little variability.
Great for memorizing specific word lists, automatization.
Right, but it might not transfer effectively to reading new, unfamiliar words in a complex storybook, or independently writing a creative story where they have to recall and apply spelling rules in a novel context. The brain learns that one specific list in that one format.
So what would a game with higher information load and variability look like for spelling or vocabulary?
Well, it might involve reading a short story where new vocabulary appears in different contexts, with varying visual cues. Students might have to infer meanings or spell words in a sentence completion task that requires them to consider the context of the entire sentence, not just one word, or consider a virtual field trip game. Students must gather information from varied sources, visual observations, audio clues, texts, dialogue, and then make decisions based on incomplete or changing data.
Like deciding which historical figure to interview based on partial clues, or which resource to investigate given shifting weather patterns.
Exactly. This higher information load and dynamic variability keeps their cognitive processes highly engaged, forcing them to adapt, infer, and apply their knowledge in a continuously changing way. It fosters deeper, more transferable learning. Much like Team Fortress 2 prevents players from going on autopilot. It demands constant cognitive engagement, not just rote memorization. It pushes them to build more flexible, adaptive mental models.
Okay, those first three scaffolding ZPD, feedback rewards, and information variability seem like solid principles for any good learning design. But you mentioned there were three more features especially optimized in action video games.
Yeah.
The ones that make them particularly potent.
Yes, these features specifically target general-purpose cognitive abilities, in particular processes that enhance attentional resources, promote flexible cognitive control, and support increased processing speed. This is where the AVG magic, if you will, really seems to happen for those broad cognitive gains.
All right, let's hear them. What's the first AVG-specific ingredient?
The first is an emphasis on processing speed, pacing. And this isn't just about how fast a game literally moves, like a frantic button-mashing exercise.
Right, not just reflexes.
No. Rather, it's about the temporal pressure placed on the player to rapidly process information in service of making critical decisions. It demands immediate planning and swift processing of incoming sensory information. Consider the contrast between those two Raving Rabbids minigames again. Bunnies Don't Milk Cows involves rapid, repeated movements, but no real-time cognitive processing or complex decision-making. Fast movements, but low cognitive pace.
You could almost do it blindfolded, like you said.
Pretty much. In contrast, Bunnies Are Addicted to Carrot Juice forces players to rapidly direct a juice stream at unpredictably appearing rabbits, needing to quickly plan sequences as their numbers and speed increase. This game stresses speed, but crucially, it also requires constant planning and adaptation under pressure. High cognitive pace.
That's a great example. It really highlights the difference between just moving fast and thinking fast under pressure. And this pacing, again, needs to be in that sweet spot, right? Linked to the ZPD.
Absolutely. It must be carefully tailored to the player's current skill level. If the pace is excessively high for a particular learner, it can actually be counterproductive, leading to frustration and disengagement, not growth. But when it's just right, pushing that optimal edge, it's incredibly effective.
And why does this matter so much? Why is processing speed so important?
Because increased processing speed is directly and robustly linked to higher cognition, to better executive functions, and to stronger reasoning abilities across the board. Studies show that playing action video games has been linked to an approximately 10% increase in response speed while maintaining constant accuracy levels.
So it's not just about acting faster, but about processing information and making decisions faster, more efficiently, and without sacrificing precision.
Precisely. It's cognitive agility.
Okay, let's translate that pacing principle to the elementary classroom. Think about a game for number sense. A slow-paced game might ask a child to drag and drop numbers to order them, plenty of time to think. Fine for initial learning, but not pushing speed.
Right. A high-paced game, however, might flash a series of numbers on screen and ask the child to rapidly identify the smallest or largest within a very short time frame, maybe just a second or two before they disappear.
Or mental math, maybe? Quick sums appearing, hit a target score before a timer runs out.
Exactly. Forcing rapid calculation and decision-making. Or maybe a digital sight word recognition game where words flash for only a fraction of a second, compelling instant recognition, not sounding out. This kind of pacing demands immediate processing and quick decision-making under temporal pressure, much like those bunnies needing to be juiced. It trains the brain to extract info, decide, and respond much more efficiently.
Builds that cognitive agility you mentioned. Okay, AVG ingredient number 2.
The second AVG-specific feature is the ability to encourage model-based learning. We touched on this with feedback, but it deserves a deeper look because it's fundamental for transferable knowledge. This refers to the learner's capacity to build rich internal models or mental frameworks to truly understand the underlying structure of the game or the learning domain, rather than just memorizing specific action sequences.
Going beyond just stimulus response.
Way beyond. The source uses the two-step reinforcement learning task to distinguish this from model-free learning scientifically. In model-free learning, you essentially form habits. Actions that consistently lead to a reward are reinforced, making you more likely to repeat them, regardless of the overall game state. It's like saying, this button worked last time, so I'll do it again, without really understanding why.
Just repeating what worked before.
Right. Almost reflexively. In contrast, a model-based learner uses their acquired knowledge, their sophisticated model of how the game world works, to make truly informed decisions. If an action sequence leads to a reward, they don't just repeat it blindly. They analyze why it worked and use that understanding to predict future outcomes and plan new actions, even in situations they haven't seen before.
It's like knowing which lever opens a door versus understanding the mechanism so you can figure out any similar door.
Perfect analogy. This form of learning is cognitively more challenging, more effortful because it requires active thinking and hypothesis testing, but it leads to what the source calls graceful generalization to new, novel situations. Model-based learning is positively correlated with stronger cognitive control, better working memory, and it's more prevalent in youth, suggesting it's a developmental skill that can be fostered.
And AVGs encourages how?
Their inherent complexity and dynamic environments basically force players to look for patterns, test hypotheses, and build a comprehensive structural understanding to manage the environment effectively. You simply can't succeed for long by just memorizing. You must understand the system.
Let's apply this to elementary social studies again. Community roles. A model-free approach. Memorize jobs. Firefighter fights fires. Teacher teaches. Maybe a multiple-choice quiz.
Simple matching, whereas a game encouraging model-based learning might present complex scenarios. A flooded street, organizing a town fair, cleaning up a local park. Students would need to understand the interconnections between roles, how the planner, construction worker, emergency services, volunteers, all need to coordinate for the flood and predict actions and impacts to solve the problem.
The game doesn't give the right sequence.
No, they build their own internal model of how a community functions, its moving parts, and apply that flexibly to new challenges. Just like an AVG player learns the structure of their world to make predictions. Or in science, instead of memorizing plant parts, model-free, they design a terrarium, model-based, understanding the relationships between light, water, soil, and adapting based on feedback.
Okay, makes sense. Loading up that deeper understanding. What's the third AVG-specific feature?
The third, and this really loads on control processes, involves game features that load on control processes, specifically multitasking and flexible attention. Action video games constantly require players to manage multiple goals simultaneously and gracefully recover from distractions or interruptions. Think about Unreal Tournament. You have to simultaneously move quickly, avoid getting hit, seek resources, track multiple enemies, aim accurately, shoot, and avoid falling off ledges all at once in a fast-changing environment.
Yeah, that's a lot to juggle. Way different from Tetris.
Absolutely. While turn-based strategy games also involve multiple goals, they differ fundamentally in the pace at which those goals need attention, allowing for much more deliberate thought. AVGs demand concurrent processing under pressure.
And that NeuroRacer study you mentioned earlier really drove this home, didn't it? The multitasking group got the broad benefits the single-task groups didn't, even at the same difficulty.
Exactly. It powerfully highlights that it's crucial to scaffold difficulty to load on control processes like multitasking and flexible attention rather than just pure execution speed for a single task. The latter is much easier to automatize, which, as we've learned, limits broad cognitive enhancements. It's about making the brain think harder in a complex way, not just act faster in a simple one.
And the flexible attention part. Switching between modes.
Right. That's the other key piece. The ability to appropriately switch between two main modes, distributed attention and focused attention. Action video games constantly demand that players broadly monitor the entire scene, using divided attention to scan for new threats, opportunities, environmental changes.
Keeping an eye on the big picture.
Yes. While simultaneously intensely focusing on a specific target, using focused attention, like aiming precisely at an enemy's weak point or navigating a tricky jump. The bunnies are addicted to carrot juice minigame again. Monitor the periphery for new rabbits, divided, then quickly focus fire on one specific rabbit, focused.
That constant switching back and forth.
Yes, that constant fluid switch between broad monitoring and intense focus, often under time pressure, is precisely what trains and strengthens attentional control systems. This mirrors tasks like the useful field of view, UFOV, and multiple object tracking, MOT tasks, both of which are similar to AVG demands and consistently show improvements when trained.
Okay, elementary connection time. Multitasking and flexible attention in a kid-friendly game.
Well, maybe that virtual classroom management simulation idea. You're the teacher, simultaneously monitoring different student groups, divided attention, responding to a raised hand, focused attention, checking the timer, divided, requires distributing attention and quickly focusing.
Or the science lab game. Tracking multiple experiments, divided, then focusing intently on one rapid reaction to record data, focused, deciding which needs attention next. Multitasking.
Exactly. That mirrors the demanding, rich, dynamic environments of action games, effectively training crucial cognitive control that translates directly to real-world learning and navigating complex academic and social situations. It trains their brains for the busy, multifaceted nature of daily life.
And this source mentioned something about the richness of the world mattering here. It's not just like isolated lab tests.
That's a critical point. In AVGs, this sophisticated attentional control is coordinated within genuinely complex dynamic environments. Events like enemies appearing might be unpredictable in time, but they're often not random in location. They burst out of logical places like windows, doorways, cover, not thin air. This means efficient performance involves not only allocating attention, but also strategically using relevant background knowledge and context to decide where to direct attention.
So you learn the patterns of the world to anticipate.
Precisely. If you detect something in the periphery, you quickly focus, identify it, decide on action, monitor consequences. Attention is tightly coupled with background knowledge and evolving goals. It requires complex decision processes over more elaborate and richer representations than in a simple, abstract lab attention test. That's why AVGs are often more effective than training interventions on isolated skills. They train the skill in context.
Okay, wow. So let's try and pull this all together. What's our big overarching takeaway from this deep dive into game-based learning for elementary educators? It sounds like it's not about just finding one magic bullet, like making a game faster or just making it harder.
Definitely not. It's truly about understanding and applying the entire secret recipe, the right combination of ingredients, working in concert.
So recapping, the 3 general principles for any effective learning are:
1. Establishing and adapting to the zone of proximal development through adequate scaffolding of difficulty, focusing on cognitive load. 2. Implementing robust reward structures and appropriate nuanced feedback, considering model-free versus model-based goals. And 3. Balancing information load with relevant, context-rich variability to prevent automatization and promote transfer.
Right. And then the 3 AVG-specific ingredients that really optimize cognitive load and drive those broad enhancements.
4. A strategic emphasis on processing speed through effective pacing, pushing cognitive agility. 5. Actively encouraging deep model-based learning to build transferable understanding. And 6. Incorporating game features that constantly load on essential control processes like multitasking and flexible attention trained within a rich context.
That's quite a recipe. 6 key ingredients working together.
It is, and this raises an incredibly important question, one that I hope resonates deeply with you listening. What's the ultimate goal here? It's certainly not just about improving game scores or simply making learning fun, though engagement matters. It's about intentionally designing experiences that target these fundamental control processes, encouraging the construction of rich internal models that can be flexibly applied to new and unpredictable situations, and thoughtfully manipulating variability in the learning environment to prevent rigid automatization and foster truly deep, generalizable learning.
Because the research links these cognitive improvements directly to academic success in kids, right? Beyond just the game itself.
Yes, there's a clear and direct link. These foundational skills, managing attention, processing info quickly, building adaptable mental models, adapting to change, are absolutely critical for young learners. Critical for navigating the increasingly complex academic landscape and the multifaceted challenges of the real world.
You came to us as an elementary education major, newly interested in game-based learning. maybe even a bit skeptical of its deeper potential. Hopefully, this deep dive has given you some genuinely surprising and practical insights into why certain types of games are so uniquely powerful, and crucially, how their underlying design principles can profoundly inform how we approach learning in the classroom, whether with screens or without.
It's about understanding that the very same cognitive principles that make a compelling action video game irresistible can be harnessed to create incredibly effective and truly transformative learning experiences. Experiences that genuinely prepare young minds for a complex, ever-changing world.
So the provocative thought to leave our listener with.
If we connect this to the bigger picture, consider how we might intentionally design or select any learning activities, digital games, hands-on projects, classroom debates, whatever, in the elementary classroom. Not just aiming for fun or educational in a vague sense, but specifically crafting them to challenge these control processes, encourage model-based learning, and maintain appropriate information load and variability. How might thinking like a game designer fundamentally change how young learners approach new challenges, cultivate a genuine love for complex problem solving? And what profound implications does that have for the future of education itself?
That's a lot to mull over.